All right, Thermo 1 class. Let's come to order here. We got a rowdy bunch in the room, which is good to see. Good to be back with you live here. Let's see. So our schedule is being displayed. So this is November 10th. My goodness, the semester is waning quickly. We had a short lecture on Chapter 8 on the 3rd, and then the 5th was a full-blown lecture on Rankine Cycle, and then this is our third one on the 10th, and we go the 12th and 17th, and then we jump to Chapter 10. So there is a bunch of information on this Rankine reheat cycle. I would caution you, this stuff seems really, really simple at first, and each little piece is, but when we get towards the end of this thing, these problems can kind of explode and get fairly long. So this is not the chapter that you'll be getting 15 homework problems per assignment. I think you got 5 in the first one, and that's pushing it. And when we get to some of these longer problems, you'll probably get 2 or 3. So anyway, with that having been said, let's jump to the PowerPoint. And I'm going to jump in here. We've already covered some of this, but I just thought it would be good just to run back over it, get your head kind of back into Rankine cycle here. So here's our TS diagram of an ideal Rankine cycle. When we say ideal, we're not going to have any pressure drops. We're not going to have any stray heat transfer. We're going to have internally reversible processes, all that sort of thing. So, you know, just see if you can envision, say, starting at going into the turbine. So the turbine, if it's straight down, it's isentropic. If it's saturated going in, we're here. If it's superheated, we're here, whatever. We fall down to the condenser pressure. This is the boiler pressure. Boiler pressure all the way from 4 to A to 1 and potentially 1 prime. Condenser pressure down here, a very low number, hopefully. And then the turbine coming down, generating the power, and the pump going up. So that's what we got going on. Our assumptions, 1 to 2 isentropic expansion in the turbine, 2 to 3 heat transfer at constant pressure at the low pressure in the condenser, 3 to 4, got a nice isentropic pump, which means we go straight up vertically from our low pressure up to our boiler pressure. So note, it's the pump that really establishes the high pressure. The highest pressure point in a real cycle is at the exit of the pump, because then a real cycle, it's going to have pressure loss all the way through there. So that's how we get to the high pressure. We just put in a bigger pump if we want to go to a higher pressure or a stronger pump. And then heat transfer in the boiler. So we're going to heat that subcooled up to saturation and across, and then whether we go to superheat or not. So anyway, so, you know, we said about the internal reversible processes. This is for ideal, then we have real. This is what I call the pump trick, okay? And so you need to remember this, because on every one of these Rankine cycle problems, you're going to use this. So this is isentropic work. You know, that's the power, or isentropic power per unit mass. Specific volume into the pump times the delta P. And you need to make sure you can handle the units, because you got some unit conversions going on here. And we've talked about that before. And then if you have an isentropic efficiency for the pump, you divide that by the isentropic efficiency, which is going to be less than 1. And so that gives you the work that the real pump would require. Okay? So isentropic work, if it's an isentropic pump, then you're done right here. If the efficiency was 50%, then you'd have to double the isentropic work to get the real work. Okay, so that's what I call the pump trick. So make sure that you understand that. Okay, I don't know what, oh yeah, this is the area representation. So for these reversible processes, on the TS diagram, the areas under the curve represent the heat transfer. So, and it goes all the way down to the axis. So the boiler heat input is 4A1BC4, that hashed area represents that heat transfer. Now, if it's not reversible, if it's not ideal and all that good, wonderful stuff, then that area doesn't work. That only works for these ideal processes. It will require more in those cases, okay? Then this is, again, for this ideal Rankine cycle, the area under that bottom curve is then the heat rejected. So the first one is heat put in. This is heat thrown away in the condenser. And guess what? The net area is the net heat, which is equal to the net work. Okay. Been over that before. This is kind of conceptually, this is important kind of stuff. I mean, this is looking at, they're trying to find ways to thermodynamically to make the cycle more efficient. Well, let's just drop the condensing pressure, which drops the temperature, which gets us a bigger enthalpy difference across the turbine and helps our efficiency. Okay, and so that's what this is. So we start off saying, okay, we're coming out of that turbine at atmospheric, and then we're going to decrease that condenser pressure to less than atmospheric. And yeah, so we start there, and then we're going to go down to there. Well, that's all well and good, but the problem is, in order to really do that, you've got to get a colder heat sink. And so, the power plant's already sitting on the lake, and then the question becomes, how am I going to make the lake water colder? And the answer is, wait till January. It's the only thing I can think that'll work. Well, and so as point of fact, that plant is more efficient in January than it is in August, because that lake water is colder, and with colder lake water, we can get a slightly lower condenser pressure. So it's really the temperature that sets the condenser pressure. And so if you compare two units, one sitting on a lake and one just out someplace that has a cooling tower, a cooling tower can't produce nearly as low temperature water as the lake can. Okay, so cooling in the summertime, you may be lucky to get 80-degree water. Well, your lake is 60, 65, so you got 15 or 20 degrees lower. So that water-cooled plant is going to be more efficient than the air-cooled plant. And I mean, it goes back to the theory, it goes back to Carnot, I mean, it goes back to this diagram. That's just the best you can do. Now, if you come up with some eureka idea on how to make the lake colder, then I suggest you contact TVA immediately, and they will want to talk to you. If it doesn't cost them money to make the lake colder, I just don't know how to do that. So I stay here and I teach instead of getting filthy rich from TVA. So, and I suspect it's going to stay that way.
The 3 rules of real estate even apply to power plants.
I'm sorry, what?
The 3 rules of real estate even apply to power plants.
Location, 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 yeah. Yes, indeed. Okay, so, and this is just showing, now, thermodynamically, we say that by lowering the temperature at the heat rejection, that's the thermodynamic theory that lets us calculate the increased efficiency of the plant. And so, at the lower pressures, we have lower temperatures, and so we get a lower temperature during the heat rejection, and there you go. And so tends to increase, just talking through the cycles there. Okay, well, let's see, for heat rejection to the surroundings, the lowest possible condenser pressure is the saturation pressure corresponding to the ambient temperature. So see, that's what sets your condensing pressure. We said that. That's good. I'm just going to go through and explain it in my own words. Y'all can read this. Okay, so the other thing we can do is try to increase the boiler pressure. And if we do that, we have to increase the temperature, okay? And I'm just getting all kinds of phone calls today. Okay, so we've got the initial cycle has the little blue line on it. And then if we can operate at a higher temperature and pressure, we would operate up there. And so the theory here is that if you increase the average temperature during the heat addition, you will increase the cycle efficiency. Well, so this modified cycle obviously has a higher average temperature. If you had the average temperature from 4 to the dome to 1, that's going to be less than the average temperature from 4' to the dome to 1'. And so, you know, that change will certainly increase our efficiency. Now, how much, you have to run through the numbers. And of course, the caveat there is that the materials have to be able to be durable and stand up under the service. And so we are materials limited in most cases on going up much further in temperature. Okay. And this is just showing the average temperature stuff. Yeah. Okay. Oh, yeah, and the point here is made, if we do this, we have an unhappy turbine, because as we move to the left inside the dome, we get more liquid water droplets, which are pelting the heck out of that turbine. That poor little turbine's spinning there at 3,600 RPM, and all those little droplets are just billions and billions of collisions, which tend to damage it and erode the materials. So the turbine doesn't like this. Well, you got to love these animations. Okay. Well, okay, so what can we do? Well, we certainly want to use superheat. And because we see from moving from the 1 to 2 expansion to the 1' to 2', the quality goes up, the amount of moisture goes down, and the turbine becomes a much happier camper operating at 2' compared to 2. And also we get an efficiency boost because of the average temperature of the heat addition. If you compare 4 to 1 versus 4 to 1', obviously that's an increased average, and so we'll get an efficiency boost as well. Okay. Higher thermal efficiency. Yeah. So it's all good. Superheat is all good, except that you go up in temperature, and you know, so potentially more damaging to the materials. He plays with the nomenclature, but I'm telling you, in the industry, you can call them a steam generator, you can call them a boiler. They just call them boilers, man. Whatever. Okay, so reheat. Yeah, and I'm not sure what slide number is this. Yeah, we're still reviewing here, I believe. That's fine. Okay, so reheat is the idea that, hey, we do a partial expansion. Say, well, our high pressure is coming in here and our condenser pressure is over here at 4. So it's kind of like, instead of buying one big turbine, we're going to buy 2 smaller turbines. And we're going to do a partial expansion from 1 to 2. We're going to have an intermediate pressure in between those. And so we're going to then go back to the boiler and we're going to reheat with some more energy from the boiler. And then we're going to come back down again. And so by doing this reheat, we get to move, we get to really help the turbine and move closer to the saturated vapor condition at 4. So that's probably the main benefit. We do get some efficiency improvement. We get a higher average temperature. You know, if you compare the temperature, I guess we're from 6 across to 1, and then down 6 across to 1 to 2, and then back up to 3 and down. So there is some efficiency benefits as well, but I think this is done primarily to help the turbine. Okay, yeah, all right, I think we've said that. We're going to slide the little X over. There we go. Okay, so, and I think, let's see, we're going to throw, yeah, we're going to throw the equations up here in just a second. So to get the total boiler heat input, now you have to do 2 calculations, right? You got to do a calculation from 6 to 1 to get the main steam, and then you got to do from 2 to 3 to pick up the reheat steam. So that's not much, but it's just something else to consider. And then we go on back through the low pressure turbine to the condenser. Let's see. So this is just, there you go. So your efficiency then is the rate of producing work in the high pressure turbine plus the rate of producing work in the low pressure turbine. We've got 2 turbines minus whatever the pump is consuming divided by the heat, the rate of heat input to the main steam, 6 to 1, plus the rate of heat input to the reheat steam, 2 to 3. Yes, sir.
Is it ever worth considering more than 2 turbines, like having an additional reheat cycle?
There are really large units that do, but generally speaking, that's, I mean, there's TVA, the Cumberland plant at TVA, and I think they're 1,300 megawatts in one unit. That's about 10 million pounds an hour of steam production. Okay, we saw those cycle diagrams for Kingston at the start of this. That 150 megawatt unit was, what, 900, a little less than a million. And I think the 200 megawatt is like, I don't know, 1.5 million, something like that. And those are not small units. But there's 2 of those units at Cumberland, which is outside of Clarksville. And I'm telling you what, those things, they've got twin turbine lines. I mean, you could probably say they've got 6 turbine rotors, and they've got stuff all over the place. So if you get the really, really large cycles, yes, they put some additional features into them, basically to boost efficiency a little bit. And you know, I'm sure it helps the turbines too. But you know, the theory is the same, and once you understand what reheat's all about, you know, if somebody gives you a cycle that's got another reheat on there, you kind of say some dirty words because you got more work to do, but you're just doing the same stuff over and over again, you know. So, but conceptually, it's just maybe some more equipment been installed. But so for the reheat cycle, this is our efficiency calculation. We got 2 turbines and we got 2 heat input, two different sections of the boiler where we're putting heat into the working fluid. Okay, and then supercritical, we talked about that. So what we do here is when we come out of our pump at 6, man, we're pumping the bejeebers out of this stuff. What is that? That's, I think it's about 3,200 PSI. 3,200 and change is critical pressure. So you buy a pump, you buy the big boy pump, you know, and you might pump it up to 4,000. I mean, there are units, there's a few units that, I don't know if they're still running, everything's shutting down on coal these days, but used to run at 4,500 pounds of pressure. I'm telling you, that pressure is generated by that pump. So that cycle, they're probably coming out at that pump at 5,000. Because, you know, you got losses around the system and this, that, and the other. It may be even higher than that. But that's generated by the pump. And then you start heating, and from 6 to 1, you heat it up, but it just doesn't quite work. It doesn't look like it did before. You don't go through this boiling and heating water and boiling and vaporization. You just kind of have fluid. And it just kind of goes from this liquid state to this vapor state. It's just kind of, I've never seen it. I don't know what it looks like. But, you know, you miss the dome because your pressure is too high. And so, you know, you get up there at 1, which is really, really high temperature and really, really high pressure. And then we start expanding through turbines. So we go through the first turbine from 1 to 2, and we stay out of the dome. And then we go back and we reheat again, maybe to a little lower temperature, maybe the same temperature. It just depends on cycle design. And then we expand through the second turbine down to the condenser pressure. So, you know, I mean, it doesn't change the equations. It just, you know, you have to be aware that if you're above that critical pressure, you're not going to have to worry about going through the saturation dome.
It makes me wonder if it's kind of like when you have a hot skillet that you put in the sink and then dump water on. You don't really see the water bubbling, but you see all the steam coming off.
Well, that's probably not a bad analogy, you know. I don't know. You know, I've always been tempted to look on YouTube and see if anybody's ever been able to film the transformation between the at above critical pressure. There could be a video out there. I don't know. I haven't looked. Anyway, there's our little dancing blue ball.
Is this the opposite of super cool liquid going to ice? Or is that entirely different?
Well, super cool liquid. No, I don't know. I don't. Let's worry about that some other time. So no phase change occurs during process 6.1. Well, we do. I don't think that's really true. 1 is definite, or 6 is definitely a liquid, and 1 is definitely a vapor. Now the transition is different, but okay, associated with bubbling and all that sort of thing. Yeah, okay, I'll give them that. So anyway, we get up there. And because of the extremely high temperatures involved, we can get efficiencies well into the 40s, you know. But I think the power industry has not really moved. They started moving in this direction, and now they've kind of stopped. And what we're doing is for any fossil fuel generation, they're moving to a combined cycle, which is a gas turbine followed by a Rankine cycle, generating steam from the exhaust gases on the turbine. And those plants are being constructed and have been quite a few in say, the last 10 or 15 years. But we're really not seeing, in fact, we're seeing Bull Run was the TVA plant that ran supercritical, and it's completely shut down now because it was burning pulverized coal. And they're trying to get out of the pulverized coal business as quickly as they can.
It's kind of ironic to think all those people who buy electric cars to be eco-friendly are possibly getting their electricity from coal.
Well, there you go. And, you know, now, you know, the long-term view of it is that we're going to generate all of our electricity with renewables. And so then, you know, we won't have any greenhouse gas emissions from the power gen. And then we can take the electricity, which is clean, and charge the cars. And so you're not burning anything in the cars. And so now you're truly zero emission. But you're absolutely right. About 3 or 4 years ago, I was at Nissan and I sat there, they're doing this big presentation on the Leaf. And that says Leaf, 0 emissions. And everybody in the crowd's going, yeah, except for the power plant, you know, which is, you know, in Tennessee. Now, if you look at the TVA numbers, their carbon numbers have dropped, you know, drastically, you know, say per megawatt hour generated, or for kilowatt hour, whatever numbers that you want to look. I mean, they've probably been cut in half in the last 10 to 15 years. But primarily, that's because of nuclear. Watts bar 1 and 2 have come on, and the conversion from coal to natural gas in the combined cycle plants. Because when we saw, you know, we saw the coal going down like this, but then we saw the natural gas going up like this. So there's a 50% reduction in CO2, roughly, when you go from coal to natural gas. So that's what's made that, and, you know, in the TVA region, getting Watts bar 1 and 2 finished over the last 10, 15 years has been huge as well. So nuclear in this area has gone up.
Where are those two?
They're outside Knoxville. Yeah. Okay. I think this is where we wound up before. I don't know how much of a review session we've had here, but that's okay. It's all good. These were the breakdown on the subsystems by your author. The heat generation subsystem and stack on A. The Rankine cycle is B, because that's, you know, we've got our steam generation in that heat exchanger coming with the heat coming from the boiler. We got the turbine, we got the condenser and the pump. And then C is the generator. And then D is the environmental side, where we suck the heat out of the condenser and discharge it to the atmosphere somehow or the other. Okay, so for a fossil fueled vapor power. And again, when it says vapor, vapor power means that we have boiling and condensing. Gas power means that we don't have phase changes. Okay, so that's one of those code words in thermo. When you see vapor, I'm changing phases. If you see gas, no, I'm not changing phases. Okay, for a fossil fuel vapor powered plant, the most significant site of irreversibility by far is subsystem A, and that's the combustion is highly irreversible. You try to take your combustion products and blow the magic whistle and they go back into air and natural gas. You work on that. Get back with me when you get some success, but I won't expect the phone to ring. I mean, it just doesn't go backward. And the other is the heat transfer. And remember, to have reversible heat transfer, you have to have an infinitesimal temperature difference. Well, between that probably 4,000 or 5,000 degree combustion temperature and that steam temperature of 1,000, that's a pretty big temperature difference. So that's highly irreversible as well. So those two components by far make the boiler the largest generator of our site for irreversibility or generator of entropy in the whole kit and caboodle. So that's where the combustion is, that's where the heat is generated, and then we transfer it into B, which is the Rankine cycle, okay? So as such, irreversibilities occur in the surroundings. The largest, that irreversibility in the boiler is considered in the surroundings to the Rankine cycle. And so they are classified as external irreversibilities when you are concentrating on subsystem B. Okay, irreversibilities in C and D are also external irreversibilities to subsystem B, but they are minor relative to the combustion heat transfer irreversibilities in the boiler. The boiler wins the irreversibility competition by far. And detailed study of combustion is part of Thermo 2 in chapter 13. So you'll have to hold off a little bit. If you're taking Thermo 2, you get to see it next semester maybe. Okay, so irreversibilities associated with subsystem B are called internal, so because we're studying Rankine cycle. So they include the expansion of steam through the turbine. You know, once you go from that high pressure to that low pressure, you don't have that magic dog whistle that makes the steam run back the other direction. It just won't swim upstream. It's not like the salmon, you know, out there in Seattle, heading for the ocean. And of course, we have friction and flow through the pump, the boiler, and the condenser. And they are typically fairly minor. I think we saw, what, 40, 50 pounds on the reheat side. On the real cycle. We might call that up one of these days and look at the real numbers. But of these, the most significant internal irreversibility associated with subsystem B is the turbine. Okay, so isentropic turbine efficiency, which I think we've talked about, accounts for the effects of irreversibilities within the turbine. Because what? An isentropic efficiency is a comparison of a real, if we're talking turbines, a real turbine to an ideal turbine. And an ideal turbine is one that generates no entropy for the working fluid as it goes through. And so we can say the same thing about a pump. An isentropic efficiency of a pump is a comparison of an ideal pump to a real pump. And so we see both of the real turbine goes from 1 to 2, where we see an entropy increase. The isentropic turbine goes from 1 to 2s, which is the same entropy. And we put the little s on the 2 to remind us that that's at constant entropy. And then on the pump, the isentropic pump would, if we start at 3, would go straight up. And this is the isobar. So they're discharging at the same pressure, right? That's a line of constant pressure. But we see an increase in entropy and an increase in temperature a little bit on this one because it's not inside the dome. This temperature doesn't increase if we're inside the dome, right? But we just get a little bit more moisture. Here we see a small increase in temperature, and that's exaggerated. If you drew this to scale, it wouldn't show that big of a temperature increase, but you know, you couldn't see it then. Okay, and so for the turbine, it's the rate of producing work per unit mass. So the power divided by the mass flow rate of the actual is H1 minus H2. And then we do that same thing for the isentropic, and we get H1 minus H2S. And notice this is a work producing component. So the ideal is going to produce more work. So it goes in the denominator. So this fraction is less than 1, okay? And here he's just going to say, put little arrows and boxes and stuff. So that's all pretty cool. We saw that before. Okay, and now we're going to jump on the pump. And so, you know.
Go back to the equation real quick. Yeah. On the denominator, is that H1 minus H2 all of that isentropic, or just H2?
Oh, well, they both start at the same point.
Right.
So if it's isentropic, the entropy at 1 and the entropy at 2s are the same.
Okay.
Because say on the plot, it's TS, and so the horizontal axis is entropy, and so if it's constant, then that has to be a vertical line coming straight down. The 1 to 2, we have some entropy increase, and so, you know, now if you want to know what that is, you have to be given to the actual, you know, properties at 2 enough so that you can find the state, or you have to be given the isentropic efficiency of the turbine. That's what typically happens. This isentropic efficiency might be given to you as 70%. So then you calculate the isentropic, the H1 and the H2S, and then you set this expression equal to 0.7, and you solve for H2, and that tells you your exit enthalpy. That's kind of the standard problem. I mean, of course, there's always different ways to, these guys writing problems in the back of the book, you know, they stay up late and get up early trying to find a way to twist this stuff around, you know, but that's kind of the standard problem. Okay, so, you know, we have basically just the other side of the diagram now. Instead of coming down, we're going up. And this is a work consuming device. So the real pump will consume more work than the ideal pump. So the isentropic work goes in the numerator on this one, and the work of the actual pump goes in the denominator again, so this will be less than 1 when we do the division. And so, yeah, it's pretty much the same thing. You usually given information to find state 3, you know, and then we do the pump trick, right? Specific volume at 3 times what, P4 minus P3, and that gives me the isentropic work. And then if I have an isentropic efficiency, I would divide that by the isentropic efficiency. So, and then we can put all the little lines on, and we get this. So this is how we deal with the pump. We okay? You good? Okay. Okay, so for simplicity in most of our problems, frictional effects resulting in pressure reductions from inlet to exit for the boiler condenser are ignored in Chapter 8. So we don't, typically there may be one or two problems back there that tell you something, but typically not. So the flow through those components is assumed to occur at constant pressure. Okay. Okay, so here's big, this is the second of our big ideas that get incorporated into the real power plants. This is called the use of regenerative feedwater heaters, or the regenerative cycle, or the regenerative modification to the Rankine cycle. So you see all kinds of different terms. So the full-blown cycle is a regenerative reheat Rankine cycle. So now we're going to put in regeneration. We already put in reheat, and then we put them all in together and give you a problem that takes you 2 hours to work. That's kind of where this goes. Or longer, you know. If I give you the real cycle, which, you know, I did in my steam power plants class one time, I made up all, well, I gave them that, I don't know, the first or the second diagram, and I made them write out the thermodynamic analysis for like 8 feedwater heaters, 3 sets of pumps. Oh man, those people were hating me like crazy by the time they got through all that mess. So it's probably a little certainly over the top for Thermo 1. But, you know, I mean, once you understand what you're doing, you can certainly do it. It's just a matter of spending enough time to work around the cycle. Okay. So what the regenerative cycle is all about is increasing the average temperature during the heat addition. Well, okay, so if you don't change the steam exit conditions, you know, let's say we have 2 cycles. One has regeneration, one doesn't. And we're going to keep the exit steam conditions the same, temperature and pressure. What could we do to increase the average temperature during the heat addition? And the answer is put the water in hotter. Put some heat, move some heat around in the cycle to heat the preheat the feed water with energy from the cycle before it goes back in the boiler. Because if let's say the water was going in before at 250 degrees. Well, all of a sudden we put a bunch of feed water heaters or stuff in and we boost it to 600 degrees. Well, if I start at 600 and go to 1,000, what's my average temperature? You know, I mean, you could do a time-weighted average, but say it's 800. Well, if I start at, let's say, 200 and go to 1,000, my average temperature is 400. So see, I can increase my average temperature during the heat addition by increasing the temperature of the feed water that goes in the boiler. That's the whole game. Now, let's be creative and figure out how in the world can I move some energy around inside the cycle in order to do that? Because the thermodynamic theory tells me I will get more efficient if I do that. So that's what we're up to here. In vapor power plants, both open and closed feed water heaters are typically used. Okay, and so now I put in these 2 slides and I will, whoops, there. I'll send out a revised presentation. This is cutting, I scanned these pages in your textbook, so these pictures are directly out of your textbook, and I just wrote up the slide. So this would be a, oh, you know what? That's a closed heater. Crap. Well, just a second. That's coming in, that's not mixing. Well, these are both closed heaters. Well, crap. I wasn't paying attention. I was moving too fast this morning. Don't look at this picture. Hold on. Oh, Lord of mercy. I did this in the last few minutes before class. Let me see. What do I want? I want this guy. But I can't see anything. Just a second. Oh my. Google Images. See, I had done this with once this morning, and I said, no, I'm going to do it from the book. Aha. Oh, look at all this wonderful stuff. This one, well, this one's pretty good. Okay, so this is an open feedwater heater. You say open FWH, open feedwater heater, I promise. In fact, just copy image. Well, shoot, we'll just fix this right here. Nothing like doing your slides before a live audience, is there? I'll find a better one later. But anyway, this is the open feedwater heater. So we take some steam from someplace. So this is showing from the exit of the high pressure turbine. And then, so we take the rest of the steam in this simple cycle and put it into the low pressure turbine. And then we take whatever steam extraction steam, and we just dump it in the can. And we take here is our condenser. So this is the low pressure steam. We condense it, say, with lake water. It's maybe 100, 110 degrees. We pump it into this open heater, and we dump a bunch of steam in there, and basically we heat it up. And so what pressure theoretically would this open feedwater heater operate at? It's controlled by the extraction pressure, okay? So our typical assumption, unless we're given other information, is the pressure of this steam exiting the high pressure turbine. We'll take some of it and most of it probably into the low pressure, and the rest of it comes over here. And so this open heater will operate at this P2, okay? And so you've got steam, whatever condition you're coming out at tube dumped in here. So you got a certain mass flow rate at 1 times an enthalpy at 1. You got a mass flow rate at 5, which is the feed water, a certain enthalpy, and they mix together and you get the total mass flow out at 6. And because this is a lower pressure than the boiler pressure, you always have to have a pump after an open feed water heater, okay? And in fact, let me, what number is this? This is 52. Let me go back here and let me show you on the real cycle. If you go back here, see, look at all these feed water heaters. We got 7 of them. Look at this guy. It doesn't look quite like the others, right? Because that's the open heater. And what do we have underneath the open heater? We have another set of pumps. Well, they show, yeah, and they put 2 because, you know, one of them is likely to break down at some point and they don't want to shut it down. So that, you know, if they need 1, they put 2 so they have a spare so they can do some maintenance. But you see, let's see, it really doesn't, it's not giving me a pressure. It's not. See, it doesn't give me a P. I wish it gave me the pressure here. Well, let's see, do I get a P over here? It's not telling me the pressure coming out of these pumps, but the boiler pressure is 1,815 PSI. So I would say this is probably 2,300 pounds coming out of those pumps at any rate. But you see, so coming out of this open feed water heater, because I have to have pumps. Now, these are closed heat exchangers. So see, this is a big pipe and it comes up and then the water goes through tubes and steam is condensing on the outside, et cetera. And so all of this is enclosed in tubes all the way to the boiler, okay? All right, let's go back. We were like 50, yeah, we were here. All right, so that's the open heater where the steam and the feed water actually mix together. And then this is the closed feed water heater, and that is a real picture, or that is the correct diagram. So you see the feed water comes in, it stays inside the tubes, and then it goes out. So there's no mingling, there's no commingling with these streams. Extraction steam comes in, it condenses on the outside of these cooler tubes, condensate falls down in the bottom, and now they're showing a pump. So this is one possibility. I guess the figure I deleted showed this thing. You can also take this back to a lower pressure feed water heater. Let's go back to that diagram, see if they show that on the Kingston diagram. Yeah, right here. Okay, so you see over here, the number one heater, we've got 47,710 pounds an hour at about 719 degrees coming into this thing. This line on the bottom, this is the condensate coming out. Well, see, this heater is operating at a lower pressure. Not sure what pressure. Is that? I don't know, but the pressure falls because, see, this is the highest pressure extraction, and it goes into this one. So on the shell side, I have lower pressure here, so why do I pump it? I don't. I just let the pressure difference between the feed water heaters move the condensate back. So say here's my 47,710 pounds an hour. It's now at 456.2 degrees, and it's coming back, and it flows in to this heater, okay? So this heater is receiving 82,280 pounds of steam from the number 2 extraction. And so my mass flow rate coming out of here is the sum. It's 47,710 plus 82,280, which I guess is 129,990 pounds an hour here. And then whatever the amount of extraction steam, where is it? There's another 50,000 pounds an hour. So now I'm up to 180,000 pounds an hour of condensate. And then it gets dumped into the open heater, and that's where that condensate then comes back into the feed water, okay? And then on these, it gets trapped back. And on this one, we actually pump it. So here's the lowest pressure heater, 4.37 PSI. I guess that's PSI-A, I would imagine. Yeah, absolute. And then, so I've got a pump, and then I pump it back and merge it into the feed water flow here. So it's pumping in 32,860, it looks like, to whatever flow I have. Looks like 671,950 out of here. So anyway, that's how, this is how, well, it is possible. I mean, I could put in a pump and pump this condensate back into the line like I'm doing down here. But on these higher pressure heaters, they just let it flow naturally back to the open heater, and then it joins the feed water there. Oh, you gotta love this stuff. If you're a mechanical engineer, you gotta love this stuff. Okay, so I think we pretty well talked about the two types of feed water heaters. And you just do an energy balance on these things. You know, the mass flow rate times the enthalpy in, summation of those is equal to the mass flow rate times the enthalpy out. Not very difficult. Okay, so now here's where the rubber meets the road. So this little 1 up here indicates that this is my total main steam flow coming out of the boiler. When you see that little 1 in parentheses, that's what that means, that you have the full mass flow. So the first section, or the first turbine, however you want to think about it, from 1 to 2 sees the total mass flow. But then we get to 2, and guess what? This Y represents the fraction of the main steam that is pulled out that goes to the open feedwater heater. So, you know, it depends on the cycle, but let's just make up a number. Let's say that's 20%. Okay? So then if I pull 20% of my steam out right here, then 1 minus Y represents the amount of steam that flows through the second turbine section. So if Y is 20%, 1 minus Y is 80%. Okay? And so those fractions are always written as the percent of the main steam flow out of the boiler going to the high pressure turbine. Because think about that diagram we just saw. There are what, 7 feedwater heaters. So you got 7 different extractions. So you got Y1, Y2, Y3, Y4, Y5, Y6, and Y7. And you have to solve for each one of those to solve the cycle thermodynamically. So you can say, oh man, after the second one, I'm getting tired of this, you know, but nonetheless. And so notice when you take into consideration the amount of power that's generated. So we have the full mass flow from 1 to 2. Turn on my little arrow here. All right. From 1 to 2. But then from 2 to 3, I'm going to take this 1 minus Y1 and multiply it by the enthalpy difference to indicate that I only have 80% of my mass flow. Okay, so we'll see that. And my condenser. Does my condenser see the full main steam flow? Well, no, it sees 80%. Okay, 80% through the first feedwater pump, 80% in here. But then guess what? In this cycle, I put in 80% here, I put in 20% here. Guess what? Now I've got a 1 or 100% of my flow coming out of the open heater. So pump 2 sees 100% of the main steam mass flow. Pump 1 only sees 80% of it. And you have to keep track of this all around the cycle. Okay? And so, I mean, for the ideal cycle, if we can draw the diagram, and so we go from 1 to 2, that's the first turbine section of the high pressure turbine. And then we're going to take some of that extraction steam from 2, and it's going to wind up over here at 6, right? And then the rest of the steam is going to go from 2 to 3 and expand down to the low pressure. And then I'm going to condense, and then I'm going to pump through my first pump up to 5. And then from 5 to 6 happens in the feedwater heater. And then I have another pump from 6 to 7. Okay. Now, this point A is on here as comparison to the cycle if I don't have the feedwater heater. If I don't have the feedwater heater, my steam, you say I would pump straight up here, and then I would just go in the boiler from A up through 7 across to 1. And so the point is, what happens to the average temperature during the heat addition? And the answer is, well, it goes up. Because my initial case, before I add the feedwater heater, I'm heating from A all the way to 1. In this case, with the feedwater heater, I'm heating from 7 to 1. Well, it's pretty obvious that the average temperature from 7 to 1 is greater than the average temperature from A to 1. Hence, I have increased my cycle efficiency. And that was my goal in doing this. Yes, sir?
So when you divert some of that steam, unless it's going into the low pressure turbine, you're decreasing the amount of work that's done.
Absolutely.
But so it's a balance, because so that would cause an efficiency decrease, but it's offset by the efficiency increase.
There you go.
So you have to just find why.
That's exactly right. The more you extract, the less goes through the turbine, the less work that you produce. but we're getting an increase. But we're reducing, I guess, the rate that we have to put heat into the boiler because the boiler is the main generator of irreversibility. So we're making the boiler do less. And so proportionately, we come out better in the wash between the decreased work, but the decrease of boiler heat input is greater, and so our efficiency goes up. Perfect, yeah.
That partly answered my question, but I guess I'm just wondering, so we're condensing the steam, presumably to saturated liquid.
Yeah, or maybe slightly subcooled.
And then we're pumping it, and then we're putting in the Feedwater heater. Does it go back into saturated, or is it because of the higher pressure that you're staying on the saturated liquid?
No, it stays, the Feedwater stays liquid because we are at substantial pressure. Okay. Yeah, exactly. Because we cannot achieve in that open heater, we cannot get it to boiling. Yeah, because that open heater is going to operate at that pressure P2, which is still significant. Yeah, no, that's a good question. Now, we do not boil in the open Feedwater heaters.
And I'm also guessing that the work required for pump 2, it's also offset by the efficiency gains.
Yeah, because we're pumping a liquid relative to the other energy flows at the boiler, the heat input in the boiler and the output of the turbine, these pump things are 1.5%, something like that. So the pump work is pretty negligible. And again, that's what gets compared and contrasted to the gas turbine cycle, which has a compressor. And when you go start compressing, oh, it's a whole nother ballgame. You're looking 25, 30, 35, maybe 40% of the output of the turbine. Say the compressor and the gas turbine are put on the same shaft. And so, so that poor turbine, it's driving a compressor on one side and a generator on the other side. So the generator only gets what the compressor doesn't, and the compressor gets a lot. Yeah, but that's one of the biggest, probably, at least off the top of my head, the biggest advantage of the Rankine cycle over the Brayton cycle. The gas turbine cycle is called a Brayton cycle. We'll see a little bit of that. Excellent questions. Good job, guys. Okay, so in this cycle, water passes isentropically through each of the 2 turbine stages, or steam, and each of the 2 pumps. Yeah, well, at this level, but when we get to the end of the chapter, they won't be isentropic anymore, and it just adds a couple of calculations. But at this point, we're showing that. Through the steam generator 7.1 and condenser occur at constant pressure. We know that. Mixing occurs within the Feedwater heater thereby. So that's another source of irreversibility, right? Once you mix them together, you can't get them to automatically separate. So that's irreversible. The Feedwater heater is assumed to operate adiabatically. Yeah, those Feedwater heaters are insulated. There's not much. You go to a plant, you see them, they're all wrapped up with insulation and aluminum jackets around them and all that stuff. I've got some pictures from Kingston. I'll see if I can remember to pull them out. It'll take me 30 minutes to find them. Okay, let's see. So what are we doing here? Referring to the TS diagram, heat transfer to the cycle takes place from, state 7 to state 1. I kind of already talked about, rather than from state A to state 1, which would be the case if the Feedwater heater wasn't present. So, yeah. So this is showing you what, with the Feedwater heater, we're going from 7 to 1. Okay. Which increases the average temperature of the heat addition and increases cycle efficiency. So there we go. He didn't do the little ball from A to 1. I kind of like that little ball thing. There you go. And that's compared to going from A to 1. Okay. referring to the schematic, let us follow a unit mass as it moves through the cycle. The unit mass is denoted in parentheses by 1. Okay. The unit of mass 1 enters the turbine at state 1 and expands to 2, where a fraction, y, or 20%, whatever you want to assume, is diverted into the open feedwater heater. And so we get that down there. And then the remaining 1 minus y expands through the second turbine stage to 3, is then condensed to 4 and pumped to 5, where it enters the open feedwater heater. Okay. Now, I mean, I'm using this 20% just to have a number. You know, when you work the problem, you solve for the y. Okay, that's part of the problem solution. So when you get to 1, don't automatically write down 20% because that's just the example I used in class. Okay, the fractions y and 1 minus y entering the feedwater heater at states 2 and 5 respectively mix within that component, giving a single stream at state 6 and recovering the unit of mass to 1. So these things then, algebraically, you add them together and they turn back into 1. Bingo. The unit of mass 1 at state 6 is pumped to state 7, coming out of that second pump, and it goes back to the boiler or the steam generator and gets, then the heat transfer goes in and we generate steam and, you know, we come back. There we go. So, any questions on that? So, you know, in terms of people making mistakes over the years, there's probably more mistakes made by not keeping track of the proper fraction of steam that you're dealing with through a particular component. Because like I said, you will work problems probably with up to 3 feedwater heaters. So you'll have a Y1, a Y2, and a Y3, and you just have to keep track of all of that and use the right multipliers in the equations. Okay, so applying steady state mass and energy rate balances to the feedwater heater. Let's see, not very good. Well, so if you look at it, what do we have? We have Y coming in. So Y times what? H2 is coming in. And then we have 1 minus Y times H5 coming in. And then all of those have to equal 1 times H6. That's the equation. Okay? So you do that and then you solve for Y. And so if you multiply across, I wish he would have shown the math on this. So you're going to have a Y times H2. And so the H5 is going to come over. So anyway, you're going to have what? Y times H2, 1 minus Y times H5 is equal to H6. And when you do the algebra, you can easily solve for Y. Okay. So that will then tell you with that extraction fraction, fraction Y known, mass and energy rate balances applied to the control volumes around the other components give us the following. And so you get for the turbine, well, you put the multiplier out in front of the enthalpy difference, right? So the multiplier going into that first turbine is 1 because you have all of your steam together. So you get the full enthalpy difference, H1 minus H2. But that second stage, you got H2 minus H3, but you don't have the full mass flow. Say in our example where we said 20%, you only have 80% of that work because you only had 80% of that mass flow. And so you put that 0.8 in front of the H2 minus H3. And notice that we're calculating this work per unit mass of main steam flow. So that's W dot turbine divided by M dot 1, which is the main steam flow out of the turbine. Okay, so it's all being related back to that. Okay, so that's the turbine work. And then for the pumps, for the total pump work, well, H7 minus H6, that pump 2 handles the entire mass flow. So that fraction is 1, so we don't have to write it. But the pump 1, that H5 minus H4, it's only seeing 80% of the flow. So we only take 80% of that enthalpy difference and we add it on to the other one. And then that is the rate of doing pump work per steam flow out of the boiler in M dot 1. Okay, so you just got to, you know, kind of keep your head straight when you do the calculations. And for the steam generator, well, it's just, we got the full mass flow through there, so it's just H1 minus H7. Okay. And for the condenser, we take H3 minus H4, but we only take 80% of it because that's 1 minus, or whatever our extraction fraction is. It would be 1 minus that times H3 minus H4 as the heat flow rate per unit mass out of the boiler at location 1. Okay, cogeneration, I'll tell you what, I think I'm going to stop right there and let's see. Yeah, I think that's pretty good. We'll come back next time and I'm just going to, I'll send you some more problem assignments to look at and we'll spend most of the next class just working through problems so you kind of get the gist, the feel of how this stuff goes. Okay, you guys have a great rest of the day and we'll be back here on Thursday. Be looking for your emails.